In this module, we will consider work and energy. In principle, all physical processes can be described solely in terms of forces and their effect on objects. But even relatively simple systems can be difficult to solve by relying only on forces and Newton's laws. It turns out that Newton's third law allows for two simplifying approaches to understanding physical processes, both embodied in what are called conservation laws. The first of these is conservation of energy. In order to understand conservation of energy, we must first define the concepts of work and energy. Work and energy have the following properties. First of all, work is done on something that moves. Work is the process by which energy is transferred to or from an object. And probably most useful right now, work is the product of the distance an object moves and the component of the force acting on the object in the direction it moves. So in the example you see, the object moving horizontal will have work done on it by the horizontal component of the force, which is the force times cosine theta. So the total work is force times cosine theta times the distance the object moves. What does Newton's third law have to do with this? Whatever was creating the force F on the block does a certain amount of work W on the block. But by Newton's third law, the block exerts a force minus F on whatever is doing work on it. So the block does an amount of work minus W on whatever did plus W work on the block. So let's recall that we said work is a process by which energy is transferred to or from an object. So it's this work which transfers an amount of energy from whatever is doing the work on the block to the block, and it's coming from the object doing the work. So assume you pull on the block via a rope and that the block slides without friction on a horizontal table. As you move to keep the rope taut, you cover the same distance d as the block. As you pull on the block, you do positive work on the block and transfer energy E equal to that amount of work to the block that manifests in its ever-increasing speed. At the same time, the block pulls on you with the same force and does negative work on you, transferring that energy from you to the block. Of course, the force from the rope is not the only force acting on the block. There is also the force of gravity and the normal force from the table on the block. However, neither of these forces has a component in the direction in which the block moves. So the force of gravity in this case and the normal force do no work on the block. Now, let there be a friction force between the block and the table, and assume you pull with just enough force that the block moves with a constant speed. Now, there is no net force on the block and no net work is done on the block. But you still do positive work on the block and transfer an amount of energy E equal to that amount of work to the block. But friction does negative work on the block and removes the same amount of energy from the block. Where does the energy transferred from the block by friction go? Well, that's a complicated question to answer. It's important to remember that kinetic friction is a macroscopic description of a very complicated set of microscopic processes. There is no simple single mechanical answer to the question, where does the energy go that's dissipated by friction? In general, the energy is transformed into heat energy and radiative energy and the energy required to do mechanical deformations. But it simply gets dissipated into a number of different forms of energy. What do we do if the force isn't a constant over the motion of the object? Well, the force can be considered to be constant if we think about a short enough distance over which it acts. So what we do is we break the total distance traveled by the object into many small distances, each small enough that the force is essentially constant over the small distance. We then calculate that small amount of work where the force is constant over that distance. We get that delta W, and then we simply sum that up over all the different little delta x's and the corresponding amounts of force over those little delta x's over the entire distance that the object travels from x initial to x final. If we make those delta x's small enough, then what we're doing is multiplying a very tiny width times the height of the curve and summing that up all along the path. That is the area under the curve of the force versus distance. And also, in that limit that those little small distances become infinitesimal, we recover what in calculus is referred to as the integral. So the work is equal to the integral of the force along the path, which gives, again, the area under that curve. Work is the product of force in the direction of motion and the displacement. But force and displacement are vectors, and we have defined this product in terms of magnitudes. We've taken the component of the force in the direction of the displacement and taken that magnitude, which is F cosine theta in the example, and multiplied it by the magnitude of the displacement, which is d. We get a scalar quantity. Well, in general, we can write this particular product of two vectors as something called the scalar product or the dot product of two vectors. We will return to this scalar product in a later module and look at it in more depth. But what is important is it's a way of multiplying two vectors together to get a scalar number. In general, our work then can be written as the integral of the scalar product of the force and the infinitesimal displacement dr along the path the object takes. This is a very complicated looking expression, and in this course you're not going to be expected to actually integrate things using this equation. But what I do want you to do is to understand what this equation represents. So in the diagram, the red line represents the path the object takes through space. And we're going to integrate the little bits of work done along this path. So at any point along the path, we consider the tangent to the path. That's the direction the object is moving. And we create a tiny little infinitesimal vector in that direction. It has infinitesimal length. And so over that infinitesimal length, the force is just going to be the value of the force at that point. We take the dot product of that force and the little dr at that point, and then we sum them up along the path to get the total amount of work. It may be a scary looking equation if you haven't had vector calculus, but you don't have to worry about that right now. Just understand the concept of what it represents. The other thing we want to understand is that work and energy have units of force times distance. That is newtons times meters, or in basic units, kilogram meter squared per second squared. And since we use this so often, the SI system of units defines its own unit for this called the joule, which is represented by the letter capital J. So capital J is the SI unit of energy. Now, if net work is done on an object, then a non-vanishing net force has acted along the path on which the object moves. This means that the object must be accelerating along its path, and so the speed of the object must change. So if we compute the work, which is the integral of the sum of all the forces along the path, and we replace the force, the net force, with mass times acceleration, and do some sophisticated mathematical operations along the way, what we see in the end is that sum of all the work done on the object is equal to 1/2 the mass times the velocity squared at the final point, minus 1/2 the mass times the velocity squared at the initial point along the path. This is a very interesting result. It depends only on some quantity that we call the kinetic energy. We use the letter capital K to represent it, but it's 1/2 the mass times the dot product of the velocity of the object with itself. But remember, the dot product is the magnitude of v along the direction of the other vector, which in this case is v, which is just all of v. So it's going to be the magnitude of v squared. So that is the kinetic energy. It's a scalar quantity. It depends only on the mass of the object and its speed, not its velocity. We see then that the net work done on an object is equal to the change in the object's kinetic energy. This is a very fundamental result, something called the work kinetic energy theorem. And it says that if non-zero net work is done on an object, its speed will change. Well, let's see what this can do for us. Consider an object of mass m moving in the y direction. Gravity exerts a force equal to mass times the acceleration of gravity acting down. Now, if the object moves down a distance h, then the gravitational force will do positive work on the object. That is, the work will be the force of gravity dotted with the displacement. The force of gravity is acting down. That's minus mg times j hat. We are getting a negative displacement of h, which is going to be represented by the vector minus h j hat. If we rearrange this, we wind up with mgh times j hat dot j hat. Well, j hat is a unit vector. Its length is 1. So the magnitude squared of that is going to be 1. So our answer is just mgh. Now, if we start with the object at rest, then we see that the work, mgh, is equal to the change in the kinetic energy, but the initial velocity is 0. So this tells us that the final velocity is going to be given by the square root of 2gh. This is exactly the result that we would have obtained using the equations for motion under a constant acceleration. We've just obtained it using a different approach. We can also consider what happens if the object moves up a distance h. Then the gravitational force will do negative work on the object. So our displacement goes from minus h j hat to plus h j hat. And if we work out the work, we get minus mgh, that negative work we said we would get. Now, if the object begins with some initial velocity, vi, and if h is the object's maximum height where the final velocity will be 0, then what we see is that the height h is going to be given by 1/2 the initial velocity squared divided by the gravitational acceleration. Again, this is exactly the same result we would have gotten using the equations of motion under a constant acceleration. We've just obtained it using a different approach.